Greetings everyone, welcome to my presentation on PyroScope AI. My name is Bhavesh Chopra and I'll be walking you through my project on PyroScope AI today. So PyroScope AI is a wildfire detection system designed to help monitor and respond to fires more efficiently. Today I'll walk you through the project, its objectives, methods and the impact it can have on early fire detection. Let's start with the problem we are facing and tackling. So wildfires are a major concern, especially in areas with dense forests or industrial zones, and they can cause massive amounts of damage to both lives and property if not detected and controlled early enough. The traditional fire detection methods rely heavily on human observation, which isn't always practical, especially in remote areas. This is where technology can make a big difference. This is where my project PyroScope AI comes in. The core idea of this project is to use artificial intelligence to automatically detect fires in real time. The system uses advanced computer vision techniques to identify fire-related anomalies. You can think of it as having a vigilant eye in the sky, which is always on the lookout for smoke or flames, and in any kind of conditions, whether it's dark, day or night, and in any kind of weather. Let's dive a little bit deeper into how it works. So this is a basic flow of the project. As you can see, it starts with data collection, goes on to pre-processing and model training. Let's talk about the data collection. The data was taken from this particular website that I've shown over here. And one of the keys to the model's success is its training data. This data set was quite diverse and it was crucial in teaching the model to distinguish between different types of fire scenarios. The model is trained on a diverse dataset of images to recognize patterns associated with fires such as smoke or the flicker of flames. So the project started with collecting and organizing images into fire and non-fire categories, sourced from publicly available datasets. The images were resized to a uniform resolution of 128 by 128 pixels to ensure consistency and reduce the computational overhead. Data cleaning involved validating the input formats and uh, using OpenCV, removing corrupted files, and normalizing pixel values to a range of 0 to 1 for efficient and stable training. The labels were assigned as 1 for fire and 0 for non-fire, and 1 hot encoded to match the neural network's output classification output. We also use certain data augmentation techniques. As you can see over here, we have the augmentation function. With this included random rotations, zooms, shifts, and flips, which were applied to enhance model generalization by simulating a diverse set of real-world scenarios. The dataset was split into training and testing with a ratio of 75% to 25% subsets, which ensures representative distributions. The augmented data was generated dynamically during training, optimizing the use of available dataset while preparing the model for varied input conditions. As you can see, these are some of the samples of the raw dataset with the labels. As you can see, some of them have thermal imaging, which helps our model, and this is some of the augmented image outputs, and here are also some of the normalized image outputs. Let's talk about the model development. So this is the architecture diagram for our model. The model begins with a separable convolution layer with 16 filters and a kernel size of 7 by 7, which was padded to maintain the input spatial dimensions. This is followed by a ReLU activation function for non-linearity and a batch normalization layer to stabilize training and accelerate convergence. Finally, a max pooling operation with a 2 by 2 pool size reduces the spatial dimensions, which extracts the dominant features which we're looking for in these images while reducing the computational complexity. The second block over here, as you can see, follows a similar flow, but with 32 filters and a smaller kernel size of 3 by 3. And the ReLU batch normalization and max pooling ensure the effective feature extraction while maintaining stability during training. And this section contains two sequential separable convolutional layers, each with 64 filters and a 3 by 3 kernel size, interspersed with ReLU activation and batch normalization layers. The dual convolution layers help capture more intricate patterns and relationship in the data. Again, a max pooling layer follows, which significantly downscaling the feature map dimensions while retaining the essential features. Final dense layer size matches the number of classes, which indicates a multi-class classification problem. A softmax activation function converts the output into probabilities for each class, ensuring that they sum up to 1. And finally, the model uses SGD, which stands for Stochastic Gradient Descent Optimizer, which with momentum and learning rate decay, enabling efficient training while avoiding getting stuck in the local minima. The binary cross entropy loss function is employed, suggesting this is likely a binary classification task applied to each class independently. Let's talk about the evaluation metrics. We use certain basic evaluation metrics like a classification report, which includes metrics such as precision, recall, and accuracy. We also use loss as a metric. Now let's dive into the results of our project. So these are the outcomes of the testing and the training. Let's talk about these results. The model was trained on 50 epochs, which started at an accuracy of 92% and improving to 97% by the 20th epoch, as you can see in this graph. And the final test accuracy of the model was 96.63%. And let's talk about the loss. The loss values dropped steadily from 0.35 to 0.08, which shows the model's growing efficiency in making accurate predictions. Validation accuracy followed a similar trend, as you can see the orange line over here, which increases from 95% to 96.63%, highlighting the model's strong generalization capability to unseen data. Let's move on to the confusion matrix. So the confusion matrix revealed excellent performance with one false positive for non-fire and very few for fire. Precision, recall, and F1 scores were around 0.97 for both classes. Let's look at the classification report over here real quick. The fire class achieved high recall of 0.94, ensuring most fire instances were correctly identified, while non-fire had perfect recall of 1. These results confirm the model's reliability and suitability for real-world fire detection while combining accuracy with robust generalization. So the primary benefit of this particular project, PyroScope AI, is the speed and accuracy. It can detect fires in real time, allowing for quicker response times and reducing potential damage. Imagine a fire starting in a forest or industrial setting, and with this project, it's caught early before it becomes a full-blown disaster, as it's commonly said that prevention is the best measure. So this not only saves lives but also reduces the economic impact of fire-related losses. And the best part about this project is that it's not limited just to forests. It's versatile enough for industrial settings, airports, and even residential areas. It can be integrated into existing security systems to provide an extra layer of safety. For instance, in a chemical plant, it could monitor fires in real time and send alerts to management for immediate action. And the system's adaptability makes it a valuable tool for a range of environments. In conclusion, PyroScope AI represents a significant step forward in fire detection. By harnessing the power of artificial intelligence, we can respond to fires faster and more effectively, saving lives and minimizing damage. Thank you for your time today. Please feel free to reach out to me if you have any questions.